Hello class. Today we're going to be discussing a new topic. This is chapter 29 out of the standard level book. And we're going to be learning about statistical distributions. So we're going to focus on two concepts today. One is the difference between a discrete random variable and a continuous random variable. And then within those discussions, we'll be talking about discrete probability distributions. These are sections A and B from chapter 29. So A is discrete random variables. All right. So a random variable describes the possible outcomes in an experiment. And clearly by the name, the experiment must be random. So dice rolling, coin flipping, and other things that can be deemed random. Those discrete or those random variables are generally given x as their variable. And what they are is they are the possible outcomes for a random experiment. Random variables come in two flavors. One is discrete, and the other, oh, I spelled it wrong, needs a C. And the other is a continuous random variable. Discrete really means countable. So if you can count the possible number of outcomes, you are describing a discrete variable. So typically, since they're countable, those x values, those discrete random variables, begin at 0 and then just go up from there. Things that are examples of discrete random variables would be, for example, the number of customers going into a store. The number of home runs in a game. The number of sixes you roll when you roll dice, etc. So anything that's countable is a discrete random variable. Whereas continuous things that can be measured are generally measurable items. So if you consider height is continuous. You could be 5.1728 feet tall. The only thing that limits the measurement is the degree of accuracy in the measuring tool, not the fact that the numbers that are the measures are limited whatsoever. So height is continuous. Weights, 100.567823 pounds, for example. Volumes. So things that are measured are continuous, and these then can be any real number. Whereas discrete numbers begin at 0 and then go up through the counting numbers. Internationally, these numbers are considered natural numbers, even though they include 0. Whereas in America, we call these numbers just whole numbers. So that's a little difference between the two of us. Now, a probability distribution, I'm going to move this. shows the probability of each random variable. One can imagine that if you have a graph showing a probability distribution, if it is discrete versus continuous, the two graphs would display very different things. Continuous, you'll see a curve that is continuous, and we have studied continuity. Whereas discrete, you're going to see something like a histogram. So let's do a probability histogram related to dice throws. So we're going to consider rolling a pair of dice. And one way to consider the different rolls of a dice is to consider a chart. So one die drops, it can be 1 through 6. The second die drops, that could be a number 1 through 6 as well. So when we say, if you roll 2 ones, you would then state your roll is 2. Because when we roll dice, we sum up the die, unless there's some weird game you were forced to do in a math class or something. But, normally people just add the die with the other die. And you can get the dice. And so I'm going to fill out this chart, which just represents the sum of the two numbers that you see when you roll dice. So one can look at this chart and very easily determine which rolls are most frequent and which are least frequent. If you take a look, it is hardest to roll double ones, it's hardest to roll a 2 and a 12. And the odds of rolling a 2 are 1 out of 36, because you see 36 different dice rolls up here. The odds of rolling a 12 are also 1 out of 36. Whereas the odds of rolling a 7 are much increased, because there are 1, 2, 3, 4, 5, 6 different ways of rolling a 7. You could get a 6 and a 1, or a 1 and a 6. 2 and a 5, 5 and a 2, 3 and a 4, 4 and a 3. So all of those are different dice rolls. Now a probability histogram lists the probabilities of all of these outcomes. So we have our outcome of 2, and the probability of rolling a 2 is 1/36. And I draw a bar that high. Our outcome of 3, well, how many ways do we have of rolling a 3? It looks like we have 2 different ways. So, 1,
Please pardon this
2.
announcement. It has come to my attention that some students might be trying to leave the building early before dismissal.
I don't know if you guys can hear
If
the
we see
announcement. It's
anyone
kind of funny.
leaving the building early before dismissal,
So this is
will be subject to
2:36,
any action that administration decides, including suspension.
and then a 4.
Please do the right thing and have.
Okay. So there are 3 different ways to roll a 4. So that would mean the odds of rolling a 4 are 3 out of 36. So you would label these different axes. The sum of the dice is what we're measuring, and then we have the probability on this axis. So this is a probability histogram, and it shows the probabilities of all the different dice rolls. And I could keep going. Your largest bar would be that 7 bar, which would be a probability of 6 out of 36. And if I drew the whole thing, which I'm not going to, but you would see some symmetry. because the most probable dice roll is 7, being the maximal probability, and then the 2 minimal probabilities are on the end, and you have symmetry in that. So that's something to note. From this histogram, we can take a look and find the relative probabilities. And probability notation varies depending on the mathematician doing it. So I could write the probability that my discrete random variable is 2. So I could write the probability that x equals 2 is 1 out of 36. And I can find that using the probability histogram, or I could find it using the chart that I did. I could also write the probability of 2. That's a little less rigorous notation, and even a little more informal is I could just write p sub 2. So you'll see any or all of these notations come up when you're looking for probabilities. The commonality is that capital P. One thing I'd like you to note about the histogram is that because this is discrete data, you're not going to have a continuous curve. A continuous curve would not make sense because you will never have a roll of 2.5. That doesn't make any sense. So you're always going to see bars when it is discrete. Whereas when we're talking about continuous random variables, which we are going to get to, that is going to be a more typical function curve. All right. I'd like to talk now about discrete probability distributions. All right, so let's say I told you that the sum from I equals 1 to n of p sub I equals 1. What this means is that
This is your last chance.
sorry, they're doing nonsense. The sum of probability 1 plus probability 2 plus all the way to probability n has to equal 1. So this would be all possible probabilities. And we know if we consider all possible probabilities, the sum of those probabilities should be 1, because we've considered the first probability, or the second, or the third, the fourth, etc., adding all those, because then we have considered all of our possible outcomes. Now, probability distributions can be given in a number of forms. They can be given as a table, a graph, which you've already seen, or as a function, which is kind of fun, that we can use a function to calculate the probabilities. And we have seen that a little bit already with our binom PDF. That is a function. So let's take a look at an example. And this is kind of depressing because we're pretty much towards the end of it. But let's talk about the probabilities of MPS having a snow or cold day. So a day you have off due to weather. There is a 16% likelihood of no days off due to weather. There is a 35% chance of 1 day off, a 40% chance of 2 days off, a 8% chance of 3 days off, which I feel like we had last year, and then a 1% chance of 4 days off. So in terms of setting this particular exploration or this probability distribution up, we want to consider what is the random variable. Well, the random variable is what we're measuring, the number of snow days. So I can say x, the discrete random variable, is given as the number of snow days. We can create a random probability table the table looks like this. On the top row, we have our possible outcomes labeled as x sub I, and then the probability of each of those outcomes. So 0, probability of 0 snow days is 0.16, 1 snow day is 0.35, 2 is 0.4, 3 snow days is 0.08, and 4 snow days is 0.01. So that is our probability distribution table. We can consider a graph. A graph is simply a histogram. Well, it's a form of a histogram, where here we would list the number of snow days because that is what we are measuring. And then a histogram would have frequency on the y-axis, but we would be measuring probability on this axis. And we'd probably go by tens up to 0.4. And then recall, these have to be bars because it is discrete. So the probability of 0 snow days is 0.16. Probability of 1 snow day is 0.35. Probability of 2 snow days is 0.4. 3 snow days is 0.08. And 4 snow days is barely a little bar. So that would be a graph of the number of snow days. And given both of those ways of recording the probability distributions, we can then answer questions like, what's the probability that x is greater than or equal to 2? So this is the rigorous notation. What it's asking is just what's the probability we're going to have 2 or more snow days. So knowing the notation and then what the notation means is quite important. And to find this, that's just the probability of 2 plus the probability of 3 plus the probability of 4 snow days, which is just the sum of these three, which is 0.49, which seems a little high, especially for this winter. I could also ask, what's the probability that the number of snow days is between and including 0 to 2? So then we would add the probabilities of 0, 1, and 2. So that would be over here, 0, 1, and 2, and that would be 0.81. So that's just a sense of getting a sense of notation and on context for the problem. At this point, I'd like a volunteer to come up to the front of the room to grab the Chapter 29 Statistical Distributions packets that are stacked up on the front table. If one of you could grab the packets and give one packet to each student, that would be greatly appreciated. I would at this point pause the recording. Pause the thing. All right, I would like you guys to turn your packets to page 714 and take a look at number 7. For number 7, we're going to ask ourselves, first of all, what sort of distribution this is. We have electrical components that are produced and packed into boxes of 10. 4% of the components may be faulty. The random variable x denotes the number of faulty items in the box. So x is number of faulty items. If you take a look, the probability is not given as a table, it's not given as a graph, it's given as a function. Note the different notation for combination. We write it as 10cx, and they write it slightly differently internationally. So if you take a look at this, it's a combination 10cx, and then you're taking 0.04 to the x power, and 0.96, which is the complement to the 10 minus x power. where x values are discrete from 0 to 10 inclusive. Because if there's 10 items in a box, either 0 can be faulty, 1 can be faulty, 2, all the way up to 10. All 10 can be faulty. So I'm hoping you're looking at this probability distribution and figuring out that it is binomial. That is exactly how we do a binomial distribution. So they're giving you a function that represents the probability of having a faulty item. So it says for part A, find the probability that a randomly selected box will contain no faulty component. So you have to think of the notation. Probability that x equals what? 0. No faulty components. So you can use the function 10C0, which we know to be 1. There's only one way for a box to contain no faulty items because they'll all be okay. And you would take 0.04 to the 0 power, because we want 0 faulty components, and 0.96 to the 10th power. And you will calculate then the probability that the randomly selected box will have no faulty components. Now if you look at B, the problem demands find the probability that a randomly selected box will contain at least one faulty component. Students, when you see the word at least, you should ask yourself if there's a quicker way of doing this problem. At least one would indicate one faulty component, 2 faulty components, 3, all the way through 10, and you'd have to add all those probabilities, which is a pain in the tush. So it is easier to consider 1 minus the probability of no components are faulty. Then that would say the box contains at least 1. So we exclude no faulty components. And then this is the same as the probability that the number of faulty components will be greater than or equal to 1. That's the same thing. So whatever your results from part A, which is essentially just 1 times 1 times 0.96 to the 10th, whatever that is, you can plug that in here, take the complement, and get your answer. Any questions? All right, hopefully no, because you're looking at nothing right now. So the homework is in the packet. I'm going to remind you again to do your homework in your homework notebook, not in the packet, because any upcoming homework quiz will not allow you to use those packets. From this chapter, you're going to do section A, problem 4. You're going to do section B, problems 3, 5, and 6. All right, good luck, and I will see you tomorrow.